this a bit bigger. There we go. So y, notice this is not y times 99. This is y of 99. So you take the 99 and you replace your x in the y of x function with the number 99. So you get 99 plus 10, or 109, which everybody got. So well done. Y plus c of 4, you can either find y plus c of x and then plug in a 4, or you can find y of 4 plus c of 4. Either way, you're going to get the same answer. So if we do this by doing y of 4 plus c of 4, we get y of 4 is 14, c of 4 is 16 minus 1, or 15. So we end up with 29. C of 0, you replace the x in your c of x function with a 0, and you get 0 squared minus 1, which is negative 1, which everybody got. Everyone, you guys all got the same answer, so you did well. And then the very, that one's hard to see. Yeah, I think it's right there. Okay. And then the very last problem, what is x when y of x equals 15? Is this 15 an x value or a y value? This is a y value. X values go here in the parentheses. Y values are what the whole function is equal to. So because of that, we set our x plus 10 equal to 15, and we solve, and you end up with x equals 5. Any questions? One. Any questions? Good. So today's lesson is section 3.3. It's called composition of functions. Composition of functions, or function composition. You are definitely going to want to take notes today. This is new stuff. So, when we compose, quiet down, please. Why we're getting up. Quiet down. I was very kind in letting some of you choose your seats. Don't make me regret that decision, right? Okay, so function composition is where we take one function and plug that function into another function. So it's almost like instead of finding f of 5, we're going to find f of g of x. Like we're taking a whole function and plugging it into another function. Why would you need to do this? Well, the main reason that your book gives, and as you go higher in math, you will see more and more reasons. But the simplistic reason of why you would need to do this is if you have a function and the output of that function happens to be the input of another function. So, for example, here in this little picture, they're talking about an oil slick. And they're saying, hey, if I know the radius of the oil slick based on the time, like how long after the accident occurred, so you had some sort of an oil leak, right? So for example, 4 hours after the oil leak, the radius of the oil slick was 1.5 kilometers. So, but I don't want the radius, say I want the area of the oil slick. Well, then I create another function where my input is radius, my output is area. So I take the output from here, 1.5 kilometers, and then I get the area, which is around 7. So this relates time to radius. This relates radius to area. So if I want time to area, like what's the area of the oil slick after 2 hours, then I have to first find the radius and then use that, plug it into this function to find the area. So you're kind of using the output from this function as the input for your next function. That's called composition. So what composition allows you to do is relate things together that don't have normally a direct relation. So time to radius, radius to area. Now we can relate time to area by composing the functions together. All right, so we're going to start by doing this with graphs. We're going to do some with graphs, some with functions, some with numbers. We're going to kind of mix it up a little bit today. So this first problem is talking about a swimmer. We have two graphs, graph A, graph B. Graph A relates the time that she has been swimming to her speed. So this is time in seconds, so it's just 1 minute of swimming. So time in seconds to how fast she's swimming in meters per second. So for example, after 10 seconds, she is swimming a little over 1 meter per second. All right, graph B relates her speed in meters per second to her oxygen use in liters per minute. So if her speed is 1 meter per second, she's using around 8 liters of oxygen per minute. All right, so anyway, so your job as a group is to just discuss, and then on paper, we'll do more whiteboards in a minute, but on paper right now, see if first you can find the swimmer's speed after 50 seconds. So think about which graph you're going to use that relates time and speed. Then you're going to find the swimmer's oxygen consumption at a speed of 2.5 meters per second. So you need to use a graph that relates speed to oxygen consumption. And then the last one, what is the swimmer's oxygen consumption after 20 seconds? So now you've got to somehow relate time to oxygen consumption. So take a minute in your groups to discuss all three, see if you can get an answer. So for the first one, speed after 50 seconds of swimming, are we going to use graph A or graph B? Graph A, and we just say, all right, what's her speed at 50 seconds? We go to 50, her speed is around 2 meters per second, right? All right, oxygen consumption at a speed of 2.5, graph A or graph B? Graph B. So we go to 2.5. So notice there are 4 in between, so we're going by 0.25. So 2.5 would be here, plug it in, and you get around 20 liters per minute. Last one, 20 seconds of swimming. What is her oxygen consumption? How on earth do you do this? Tony, what do you say?
Both graphs, so you can find out the speed in the first one by relating it to 20 seconds.
So plug in a 20.
You find out it's about like 1.5 meters per second, and then you just plug in 1.5 into graph B, and you'll find out it's like I think around 12 meters.
12, 13-ish, yeah. Yeah, very good. So around 12 or 13 liters per minute. Very good. All right. Did all groups get something like that for the last one? Yeah. All right. That is composition from a graph. Put the phone away, please. Okay. All right. So we're going to start. I'm not going to teach you how to do this. I want you guys to see if you can figure it out. So we have the function f of x equals 3/4 x minus 3, and g of x equals the absolute value of x. Now, don't worry about the graph yet. What I want you to do first is see if you can find what this looks like as a function. What on earth is the function g of f of x going to equal? If this is f of x, and this is g of x, what would the function g of f of x be? So take 10 seconds or so and see if you can discuss in your groups. Figure it out. Yeah, Mary. That is perfect. Now, Did any other groups get the same answer? Just curious. Only one other group, 2 other groups, 3 other groups, 4, 5. You kind of got it? Okay. So how did Mary get that? What'd she do? Let me ask you a question. Back up. If I asked you this, suppose I just asked you, hey, what's g of 5? It's the absolute value of 5. How do you know? Because you replace the x in your g of x function with a 5, right? So if I'm asking you what's g of f of x, you're going to replace the x in your g of x function with f of x. So you're going to take f of x, and that is your new x in your g of x function. Notice it's not times, you're replacing. You're plugging it in for x. Does that make sense? All right. So let's talk graphs. Without the absolute value. So let's just pretend I asked you, what's the graph of y equals 3/4 x minus 3 without the absolute value? What kind of a shape would this be? It'd be a line, right? Would the line be increasing or decreasing? Increasing, going up from left to right. What's the y-intercept of this line? Good. Hey, is that line going to be shallower than a slope of 1 or steeper than a slope of 1? Shallower, because the slope is less than 1. By the way, the equation when the slope is 1, and you know what that line is? Y equals x, right? Okay, so we're going to be a little bit shallower than y equals x. So some line, I don't know, something like that. So we've got our line. Now let's think about absolute value for a minute. What's the absolute value of 5? What's the absolute value of 10? What's the absolute value of 0? What's the absolute value of negative 5? Okay, good. So you all understand that absolute value, you've probably been taught the word distance from 0. Has anyone ever been taught distance from 0? Yes. I personally like to teach absolute value as the size of the number, or in other words, I like to use a word called magnitude. And the reason I like to use the word magnitude is when you someday learn vectors, and it's despicable me, right? You know what I'm talking about? You remember vector? Yeah, vector, both direction and magnitude, right? Well, what does magnitude mean? It just means size. How big is the thing, right? How big is the number negative 5? Well, it's 5 units big, right? Just the negative just tells you what direction it is. But the 5 is how big it is. So the absolute value, I like to think of it as a magnitude. It's the size of the number. So when your number is negative, the absolute value essentially just makes it positive, right? All of these numbers have positive y value. Every number from this point forward is already positive. Does everyone understand that? Because it's above the x-axis, they're all positive already. So the absolute value of these doesn't change it at all because they're already positive. But these guys are all negative. So if this number is negative 1, the absolute value is 1. This number is negative 2, absolute value is 2. Negative 3, going to 3. Negative 4, going to 4. And what it does is it takes the part of the graph that's below the x-axis and flips it up above. We are going to study 3 main different types of graphs, 4 main different types of graphs over the next couple of weeks. One of them that we're really going to study is absolute value, but not today. Today is just like a little intro. Hey, by the way, absolute value. But anyway, we will spend a whole day doing nothing but absolute value graphs later on. Okay. All right, so anyway, so there's your graph if you want to see it. Okay, So composition is actually an operation, and it involves taking a function and plugging it into another function. We've already done this. We just did it a minute ago. Shoot, it's all connected. Okay, I'll just have to leave it. We just did it a minute ago, but what I want you guys to do is, on your whiteboards, if f of x is 3x and g of x is 2x plus 1, I want you to see if you can figure out f of g of x and g of f of x. Take a minute, work together, see what you can figure out. Don't have one person take over the whole thing. Work together. Slowly. So f of g of x means you're going to take your g of x function and plug it in for x in your f of x function. It's f of g of x, so g of x is what gets plugged in for the x in your f of x function. So f of g of x would be 3 times 2x plus 1. Now, there is another way to think about this. And if this works for you, great. If you don't need it, you don't have to use it. But what I sometimes teach students to do when they're composing functions is, so we have f of stuff, right? F of something. So I know, since my outer function is f, if I write my outer function, whoops, I got it here, I'm going to do it. If I write my outer function, my f of x function, but wherever I have an x, I just put a parenthesis. And then I say, all right, what goes in the parenthesis is whatever is in this parenthesis, right? So what goes in the parenthesis is your g of x function, right? 2x plus 1. So you take your outer function, put parentheses wherever you see an x, and then what goes into the parentheses is whatever inside of here. I don't know if that helps or not. But that's another way to think about it. So once we clean this up, we end up with 6x plus 3. Domain. If I have the function y equals 6x plus 3, what does the graph look like? It's a line, right? The domain of any line, unless the line is vertical, apart from vertical, all other lines in the whole world have the same domain. And remember, a domain is an interval. It's all the x values for which the function is defined. Meaning all the x's where if I plug in the x, but if I plug in a number for that x, I get out a number for y. What is the domain of this function? Okay, infinity is a number. I want an interval from what to what? Negative infinity to infinity. All real numbers, right? So for our domain, you can write negative infinity to infinity. By the way, when we write interval notation, if you want to include the endpoints, you put brackets, but we can't bracket infinity because it's not even a number. How can you include it, right? It's always moving. So you can't bracket infinity. You could also write it like this. That's called set notation. Or there's a shorthand for the set of all real numbers, which I taught third period. And fourth period, there is a group that actually knew it already. I'm so impressed. Which is R with a double bar. So that's also a way of writing the set of all real numbers. I don't care which way you do. This, you know what, I do care a little bit. I prefer this just because interval notation gets used so often and forever that it's a good thing to really know. Yes?
Can we say all real numbers?
Can you write the words all real numbers? You could, and I would accept it, but I would like you to learn one of these instead because we are above and beyond writing the words all real numbers. Okay? We're going to use math notation. All right. So now let's talk g of f of x. G of f of x means you're going to do the reverse. You're going to take f and plug it into your g function. So I am going to take my g and put a parenthesis where the x is. And then what goes in the parenthesis? 3x. It's your f of x function. So my, whoops. Oh, that's a really weird 3. My g of f of x equals 6x plus 1. What's the domain of y equals 6x plus 1? All real numbers, right? Which we write as an interval of negative infinity to infinity. Good. All right, any questions on this? Nope. All right. Now we're going to learn how to do this with numbers. So instead of with functions, we're going to do it with numbers. There are two very different approaches for doing these with numbers. What I think I'd like you to do is every group just in your seats, take about 30 seconds and just do number 1 and like do it silently for a minute for 20 seconds and then check with your group members and see if you get the same answer. I know you haven't been taught it yet, but just do your best, see what you get. So you can decide which way you like best for these. I personally like to do, when I have to do composition and I'm not plugging in a function, I'm plugging in a number, I like to work them in what's called inside out. So I start from the inside, I find that, and then I plug that into the outside. I do them inside out. So what I would do for this first is I would find what g of negative 3 is. So I'm working inside out. Inside out. All right, so g of negative 3 is negative 3 plus 1, which is negative 2. So g of negative 3 is the same thing as negative 2. So now I'm going to plug negative 2 into my f function. So now I do f of negative 2, right? Whatever you found for this, you plug into here, and you get 2 times negative 2, which is negative 4. How many of you got that? Fantastic. There's a different approach. You don't have to do this, but I just want you to know that it works. If instead of working inside out, suppose you really love composing functions, you could find f of g of x first, find the composed function. F of g of x means I'm plugging g in for the x in my f of x function, so I'd have that. And then if I want f of g of negative 3, I just plug a negative 3 into here. 2 times negative 2 is negative 4. Voila, right? I personally tend to do it this way. I tend to work inside out. But if you want to find the composed function first and then just plug the number in, you get the same answer as long as you do it correctly. All right, I'm going to give you about another minute to find g of f of 2 and h of g of 5. Okay, g of f of 2. Let's do inside out. What's f of 2? What does f of 2 equal? Does everyone understand that f of 2 is 4?
Yes.
Yes? Okay. So now what we do is we take that 4 and plug it into our g function. And what's g of 4? 5. Did everyone get 5? Yeah? Good. All right, last one. H of g of 5. So we find g of 5. What's g of 5? 6. And then you find h of 6. So you end up with 6 plus 2 over 3, or 8/3. All right. Any questions, any problems, any troubles, concerns? Everyone's good? I'm trying to match eyes with everybody. Middle group here is good? Yes? Okay. All right. We're going to do the exact same 3 problems except we're going to do it with x's, no numbers. So you did this a few minutes ago, f of g of x and g of f of x. What you didn't do, which is super fun, is the little challenge problem here, h of x. Not only do I want you to find it, I want you to simplify it. All right? Okay, I give you a couple minutes. I would like 4 and 5 on your whiteboards. Would you like to try to put this one on your whiteboards as well? All right, all three. So, for the first one, remember, composition is not multiplying. Composition is substitution. You're substituting the x in your f of x function with the whole g of x function, right? So think of it as my f of x is 2 times something. What do I put in for that something? In this case, it's g of x, which is x plus 1. So f of g of x, if you distribute, is 2x plus 2. All right, does everyone feel pretty comfortable with that part? Okay, g of f of x, same thing in reverse. My g of x function is something plus 1. What goes into the something? It's whatever f of x is, which is 2x. You don't even need the parentheses, so you just write 2x plus 1. No, you got that right. Oh. It's time for h of x. So, h of x, I'm going to put parenthesis where my x is and write everything else. Yeah. What goes in the parenthesis? H of x, which is x plus 2 over 3. I think every single group got that. So beautifully done. Now it's fun with fractions. So there are 2 different approaches for simplifying what's called a complex fraction. Whenever you have a fraction inside of another fraction, it's called a complex fraction. There's a longer way and there's an easier way. No one ever teaches the easy way. I don't know why. Everyone always teaches the long way. I'm going to show you the long way, and I'm going to show you the slightly faster, easier way that I always use and have loved for many years. So the long way is to find an LCD. So on top, we have x plus 2 over 3. So I need this to be over 3 so I can combine these fractions, right? So this is the same thing as 6 over 3 all over 3. So if I combine the fractions, I get 8x plus 8 over 3 over 3. Now, a lot of people make the mistake when they see a 3 and a 3 and they think the 3's cancel, but they don't, because this 3 is actually a little fraction over 1. And when you're dividing fractions, you multiply by the reciprocal, and you end up with x plus 8 over 9, right? And that would be the most simplified version. Now, I'm going to start over. So we have x plus 2 over 3 plus 2 over 3. I'm starting over. I'm going to show you a different way. Okay? Okay, this is the price method. There's actually, it's not my method. I didn't make this up. This has been around for years. But anyway, hey, if I had to find an LCD for all of these terms, what would be the LCD? What's the LCD you all found? 3. Least common denominator, right? Yeah, that's okay. It would be 3. Don't actually do it. This is a fraction. You can multiply top and bottom by the same number because this is just equal to 1, right? Does that make sense? 3 over 3 is 1. Okay. Watch what happens if I multiply the whole top by 3. I'm going to multiply the whole top by 3. What is x plus 2 over 3 times 3 equal to? X plus 2. What's 2 times 3 equal to? Now let's do the bottom. What's 3 times 3? Done.
Oh, that's so much.
I know. This is what I always do with complex fractions. I love doing this. Okay. Yes. Huh? From here to here?
Yeah.
So when you multiply, I'm going to write it down here. If I take x plus 2 over 3 times 3, these cancel.
Okay.
And you're left with just x plus 2.
And then 3 times 2 is 6.
Yep.
And then 3 times 6.
Yep.
And then you add the 2 and the 6 to get x plus 8.
Yep.
Can I use that?
Yes, sir.
3 over 3.
All right, good. We gotta move on. This is the focus of today is not how to simplify complex fractions. So, although it's a nice little book. Okay. All right. Let's see if we can do this with graphs. We did one with graphs earlier today with swimming. We're doing one now without swimming. I gotta change this graph. It's kind of silly. I'm gonna extend this up. Pretend it goes all the way up to there. I'm gonna put little like starting and ending points on these graphs. All right. So here's the thing. I know you can all find g of f of 1, f of g of 3, and g of 5. I think you can find all 3 of those. I challenge you to see if you can find the domain of f of g of x. I tell you now that not a single student in 3rd period figured it out, but I think someone in here can figure this out. All right, so you can just do it on paper. Just stay in your groups for and work in your desk for a minute. All right, so I'm actually going to start with the middle problem because the middle problem, if I label these, the middle problem is easier to demonstrate with. F of g of 3, we're going to work inside out. So first we have to find g of 3. So what is g of 3? Well, I go to my g graph. I go to where x is 3. What is the value of g of 3? It's 2, right? So f of g of 3 is the same thing as f of 2, right? Because you take this, right? Plug it in for x. So now we go to our f graph. What is f of 2? 4. Right? Input, output, x, y. Right? Functions are all input, output. You plug in a number, you get out a number. The input's normally your x, the output is normally your y. All right, so g of f of 1. So what is f of 1? What's f of 1? It's 1. 1, 1, 1. So g of 1, take this. So what's g of 1? 1. That's why I didn't want to start with that because it's kind of silly to demonstrate when it's just 1, 1, 1, 1. All right. G of 5. If you did not get this one or this one, I want you to take 10 seconds. I'm not even going to turn off the recorder and mentally see if you can figure out g of 5. All right, everyone hold up your fingers in what the answer is. Is that a 2? Okay, it's like kind of like a casual 2. Very good. All right, excellent. So G of 5, go to 5. G of 5 is 3. So we're finding G of 3. G of 3. Go to your G of X graph, plug in a 3, and you get 2. All right, one student I know correctly found the domain. Is there anyone else What do you think? 1 to 3?
I think it's -1 to 3.
-1 to 3? No one else? All right, Grace, what's the answer? 1 to 2. All right, the correct answer is 1 to 2. Now let's talk about why, and this is tricky. I don't know, I haven't looked at your test. I don't know if there's one that's confusing on your test, but we're gonna at least get a feel for it so you understand how this works. So the domain of f of g of x, when you plug stuff into your f function, the stuff you're plugging into f, those are the output values for g. Like if I wanted f of g of 3, right? I'm not plugging a 3 into f, I'm plugging what f of g of 3 is into f, right? So the input into my f function is actually the y values of my g function. So what I'm looking for then is if my g function y values go from 1 to 3. So that's the input for my f function is from 1 to 3, except f doesn't go to 3. F stops at 2, which means the final domain of this function, the values that overlap, are only from 1 to 2. It's kind of a complicated process, but the domain of f of g of x is 1 to 2. Why? Because, so I'm going to write this, domain of g. So domain of g was 1 to 5. The range of g was 1 to 3. This is what you're plugging into f. Are the numbers 1 to 3? Except 1 to 3 doesn't exist on f, so we have to, must be restricted to what exists on f. So, kind of tricky. But the big thing to kind of pick up on there is that your input for your outer function are the y values of your inner function. So, later, not now. And this is, it's high. That's okay. It's okay. So this is a review of a couple of things. This is not composition. This is to review operations with functions, multiplication and division, but it also has some really fun reviews of what do you do with exponents when you're multiplying and dividing, and a little bit of fraction review, right? So let's just make sure we're all on the same page. If I multiply two x's together with different exponents, what do I do with those exponents? You add them. And if I divide, what do I do with the exponents? You subtract them, right? Okay, so I want you to take a minute just on paper and see if you can find all four of these. I'm going to time you at 1 minute. Go. So f times g, 2x to the 3/4 times 7x to the 1/3. 2 times 7 is 14. X to the 3/4 times x to the 1/3, is that x to the 1/4?
No.
No, you got to find an LCD. So your LCD is 12. So you have 9/12 plus 4/12. 13 twelfths. Add your exponents. Be careful. F times F, 2x to the 3/4 times 2x to the 3/4 is 4x to the 6/4, which of course we would write as 3/2, right? We reduce our fractions. All right, F divided by G. 2x to the 3/4 divided by 7x to the 1/3. So 2/7 is just 2/7. So I need to subtract these. So 9/12 minus 4/12 equals 5/12. How are we doing? We having a wake-up call on fractions? Yes.
Would you need to put 2/7 x on parentheses, or would it be?
No, this is fine. It's just a coefficient. You could have 2x to the 5/12 all over 7 or 2/7 x to the 5/12. I like this one better. All right, last one. What is anything over itself? 1. With the exception of 0, right? Yeah. All right. So we are almost done. Let us just make sure we can do composition without linear functions. F of g of 4. I want you to take a minute, find f of g of 4. If you get this, we will be done, and then we can move into homework, and I'll explain what's going on.
So one of my friends is in this problem.
Okay.
One of these teachers.
Okay.
And it's just a really badly drawn heart.
So he converted it into polar coordinates.
Yep.
But if what I thought you were trying to have me do was actually solve it for y,
Nope.
I'm almost
It has no
done.
social life. Wait, you're actually going to solve this problem?
I'm almost done. Y equals, so this divided by, so yeah, 1.5 x, I can't fit it, plus or minus square root of x squared. So this would be plus this over 64, and then this is all over 4, all over 2. So my final answer, 4, 3, 6, 6 absolute x plus or minus square root of x squared plus 64 all over 8. So it's really hard to write though. It's 6 plus or minus square root of x squared plus 64 all over 8. That's the actual answer of what y equals, if you wanted it. Okay. So g of 4, 2 plus 4 minus 1 quantity squared. 2 plus 3 squared. What's 3 squared? So g of 4 is 11, right? What do we do with the 11? Plug it into f of x. F of 11. 3 plus the square root of 11 plus 5. Little quick misconception. What is the square root of 16?
4.
Is it 4 or is it plus or minus 4?
4.
Plus 4.
It is just 4.
That's square root.
The only time you put a plus or minus in front of a root is if you're solving like x squared equals 16 kind of a thing. Like when you're solving a quadratic. Otherwise, it just is what it is. It's just the positive. Good. Okay, so let me stop this, and then I got to hand out